Hello. In this video, we're going to be practicing derivation, deriving an expression for indicated variables. Practice for the AP Physics 1 and AP Physics C exam. Please remember to pause or rewind the video as necessary. Also remember to list as many of the concepts as you can think of before beginning the problem, as many of these problems often combine and link many concepts together. Let's begin. We see a solid cylinder with mass m, radius r, and rotational inertia I equals 1/2 mr squared, and a centered hole of negligible radius is placed over a rod securely attached to a smooth table so that it spins without friction. A light string is wrapped around the cylinder over a pulley attached to a block of half the mass, m/2, located at a height h above the floor. The system is released from rest after the block reaches the floor. The cylinder continues spinning. Derive an expression for the time the cylinder takes to complete one revolution after the block hits the floor. Well, first off, if the block is changing height clearly and changing speed, and you have changing omega up here as this cylinder is going to spin faster, this is clearly an example of conservation of energy, but with rotation. Remember, conservation of energy with rotation also involves a linear angular relationship between linear and angular speed. So make sure you account for that in the problem. Okay, let's go ahead and begin. Conservation of energy states that the initial energy equals the total final energy. Well, the initial energy in this case is going to be the potential energy of this block right here. That's going to fall. So potential energy of the block is going to equal a couple of things. It's going to equal translational kinetic energy of the block moving down at this point. It will be moving, and rotational kinetic energy of the cylinder. So a little bit of both, two things going on. Let's go ahead and derive into this. So this would be m/2 GH equals, the translational kinetic energy would be 1/2 m/2 v squared plus the rotational kinetic energy of 1/2 I omega squared. Okay. Now we are going to make a couple substitutions for I and omega squared. So recall, if we're going to substitute for omega, which is v over r, that means omega squared would be v squared over r squared. We're going to substitute that. So starting from the beginning, we have m/2 GH equals 1/2 m/2 v squared plus 1/2, and then the rotational inertia I is 1/2 m r squared, and then omega squared, we're going to substitute v squared over r squared. Now you'll notice a couple things happen. One, r squareds cancel. Two, the mass of the cylinder, big M, cancels. So we are left with 1/2 GH equals 1/4 v squared plus 1/4 v squared. So 1/4 plus 1/4 is 1/2 v squared. You can see the 1/2s are going to cancel there too, and v is the square root of GH. Or we can say v squared is equal to GH. We'll need one of the two there. Now, we got this far, okay? But the question's not asking us for speed, it's asking us for the expression for the time it takes. Well, the time it takes to complete one revolution is known as the period. So we're deriving essentially the period of this. Now, how is period related to speed? Because speed is what we found and solved for. So how is period even related to speed? Period is the time it takes to complete one cycle. Period, if you recall, is equal to 2 pi divided by omega. So here's what we can do. Recall that omega, okay, is equal to V over R. So we can go square root of GH over R in place of omega. And the period would therefore be 2 pi over omega, which is the square root of GH over R. That would be 2 pi over 1 times R over the square root of GH. And that is a suitable expression for the period, or the time it takes to complete one revolution. 2 pi R over the square root of GH. And just double check with the variables involved in terms, just derive an expression for complete. You know what, it doesn't say in terms of what variables, but I'm assuming in the variables given. So mass of the pulley, radius, height that it's, dropping from. So I would think it would be those variables that had been listed in the problem. But normally they give you a list of indicated variables that you're supposed to derive it. Well, if the cylinder were replaced by a cylinder of equal mass but larger radius, would the time for one revolution increase, decrease, or stay the same? Well, what do we know? A cylinder of larger radius would actually have a smaller angular speed. So think about it. If it's a larger radius, it has a greater rotational inertia, which means it's going to build up speed a lot more slowly. So it's going to have a smaller angular speed, omega. And since we know that T is not only equal to 2 pi over omega, but it's essentially proportional to the inversely proportional to omega, that means the smaller omega would mean it takes longer time. And the time would be larger. If the experiment were repeated by dropping a block four times the distance h, by what factor would this change? Well, if you look, t is equal to 2 pi r over the square root of gh. Now, 2 and a pi are constant, so just don't even worry about that. What this tells you is that t is proportional to r over the square root of h, because remember, t is a constant too. So since r doesn't change, t is proportional to 1 over the square root of h, but h increases 4 times. So the square root of 1 over square root of 4 is 2. That means the period would be half.